Bismillahirrahmanirrahim. Hello everyone. This is another ETABS tutorial. In this tutorial I'm going to show you how to perform a nonlinear pushover analysis. But before we jump to the ETABS software, let me give some background on the pushover analysis. Why we're using pushover analysis and where we should use. We usually use for the earthquake assessment and also for the retrofitting of an existing structure. Let's see, here is a capacity curve which is giving with some figures and then showing difference performance of the structure after an earthquake is happened. So the first region is we call the elastic region, and that means the structure will not happen anything. So the second part is that we call the elastic limits, so which is the region which is transferring from elastic to plastic. So maybe some small cracks or minor crack will happen. So the third one is we call the immediate occupancy, which is similar to this figure, which you can see significant cracks appears in the opening area and showing some sort of large damage or sort of some fares for the occupants. So that means we called immediate occupancy. And the last part is we call the fourth part is we call life safety, and this is the life safety, which means the structure seems be not safe anymore, but it can not take the people's life. And this one is the collapse prevention. So the crack is propagate and also damage the major part of the structure, and so it means we cannot prevent from the collapse, so we called collapse prevention area. And so finally the final picture is showing the collapse area, which is the structure should collapse and there is no possibility of the retrofitting the structure. In this picture we will not do any rehabilitation, but in other two main parts we have some level of repairing costs and also some repairing time. It's just approximate for the very simple 5-story or 10-story structure, but in case you have a very high-rise building or multi-story structure or a huge hospitals or schools, so then you have to manually calculate the repairing cost and also the scheduling times. So now we will perform. We suppose we have a structure which is an existing structure, and we want to evaluate this curve and get the curve and see when the structure will start to in this region and finally this region and collapse. So for this we have two code. We have FEMA 356, there is maybe less version also, and also AC7, both using for earthquake assessment and rehabilitation of the structure. So now for the procedure, how we can perform this analysis, we should model an existing structure. It means after earthquake has happened, you can remodel the structure, and so you do not need to design, but you should you have the earthquake data, and you can get the data and compare with the capacity curve which you model from the structure. So we will do the same things. Now we will model, and we suppose we have a structure 3 bays by 3 bays, 6 meters each base, and totally 4 meters, 4 stories, each story 3.2 meter height. Then we will define the gravity loads, and we will define the lateral loads. So that lateral load means we want to push the structure. So we suppose we can give the lateral force in case if you calculate in the present times of earthquake data, and then you can get the shear force and apply that to the structure and see the displacement, and during the displacement you can get this curve and interpret the curve. So we will just define some displacement or giving displacement, and then see how much during the displacement the structure showing horizontal reaction or resisting. So then we will perform the analysis and also see the result. So there is one thing I should say, mostly in every program when you work on, and that's linear. So we use the linear properties of material. But for earthquake assessment, with using pushover, you should define at least one kind of nonlinear behavior. So we usually use rotational hinge. We can define the rotational hinge in the middle of the column beams or end of the beam columns. Why we're using in the middle? So that means we suppose that structure will damage that beam. Let's starting in the middle. But in practical, we often see that the structure beam column, especially in the near to connection or near to end, will damage. So we define that rotational range in the end of the beam columns. Now we can go to the program and we can define model our structure. Here is one define it. Okay, let me create a new model. It's better to see how we can model a structure. That's also better. So I go back to here, and so this structure is already an existing structure, so I want to do the same for this one. So we can use metric units, and I want to use material, European materials, and also let me see Euro materials. And design code, we do need to design this structure. That means we already have designed and also constructed. So we have 4 grid in the X direction and 4 in the Y direction, and we have 6 meters length in each. In the Y 5 meters, in the X 6 meters. So we have total 4 stories, and each story is 3 point, and the last story is first story is 2.3. So using grid only, and I'm okay. Now I want to model the column using IP section 400, and I'm going to define, and the material, let me define material. We're using this material S315, so mean the yield strength is 3500, and the column we can see here comes to here. There is the IP section. If there is no IP section, we can go to define section, and I can go to IP section, and here I want to select still I or W section, Y section, input. Here is error codes, so I can select the IP section here. Let me take from 200 to 500 to 600. Now I have defined here, and I want to select the columns IP 400, and this is IP 400, this one, and I'm going to select all. So this is the 4th story. Let me go to undo and select here, because all story is uniform column, so I'm going to select all, and I define the column. So I want to select this in this 2 grids columns, and I want to assign some rotational or local axis. So I want to rotate to 90 degrees. You can see now it's rotated. So here I want to see in a 3 dimension or in a rendering. So here is now let me define the beams. Quick draw beam, and I want to select beam IP 500. This is IP 500, IP 500, and I'm going to select all, and you can see the IP 500 is defined to entire structure. If I go back to re-rendering, and you can see beam column is added. So now the next one is the secondary beam. We want to define some secondary beam or adding some lateral support for beams. Quick draw secondary beam. The secondary beam is using the moment release to end using IP 200. We select here IP 200, and here is IP 200. So how many you want in each base? So I usually use 2. I can draw. So now I finished in the entire secondary beams. The next I want to define a slab. Let me go to section, and it's called the slab section. So I want to use this slab. Is the thickness is about 200, so I'm gonna give it 150. I'm using this concrete. Okay, and I want to select this one, draw rectangular floor, and selecting this point and this point. And now the entire slab is added, so I'm going to the base. So I wanna select here 1 story, and I wanna delete this one. Press the delete, and I want to select these joints, and I want to assign a restraint is fixed. So next I want to define some gravity load. Let me define some gravity load. So for this purpose I'm gonna go to the select, and here I can select object, just floors, and here is floors, and I'm going to assign frame load, shell loads uniform, and dead load is -1 kilonewtons, 1.2 kilonewtons per square meters, and live load is previous selection is 2.5 kilonewton. So I'm going to apply it, and okay. Now I can go to the next story. You can see the load is applied, and here is. So now I want to go back, select again the that floor object. The entire floor is added, selected, and I'm going to assign shell elements. Here is going to diaphragm. So the diaphragm can control the displacements in that point in the mass centers. So we need to define a constraint or diaphragm. Now the modeling is finished. What we're gonna do is next we want to define some hinges. We can define hinge manually. Go to the section, and in the section we have frame, wall, nonlinear hinges. You can add new properties. For the steel you can select steel. Now in the properties you can select for the deformation control, you can which parameter you want, axial force, shear force, weight. But for this each section has different plastic moments, so we are not intending to manually calculate each one, but we're using ASC 7 or FEMA code, so the program will automatically define based on the given section. So what we're gonna do is we want to go to the here, select, we can go to the object, and I want to select beams. Now the entire beams, secondary, primary, all beams selected. So what we're gonna do is we're gonna go to frame here, and here called hinges. Now I want to use the automatic method, so I want to give 0. It means 1 or I side or J side. So I'm going to add. Here is the given code, the table. In case you can check this table, and you will see the IO each parameter is giving for you. And also we have FEMA. In the previous one was FEMA. Now there is another code as well. So this was the latest version. We're gonna using this 17, and we selected beam. So that means we're using the beam is caused the deformation based on the flexural behavior or moment. So we're selecting the moment, and you can also check the isostasis behavior of that beam. So that's we are isotropic. We have also kinematic. We also tachyda and pivot. Another one also degrading. You can select any of them you want. You can just for the comparison you can use difference of. Let me define the for this study kinematic. So means no parameter required for this step. It means when I use Takeda, or let me use kinematic, and I'm going to select kinematic, and we're going to call it OK. So the second part is which the other end is giving 1, using the same kinematic and giving 2, and I'm going to call it OK. So the hinges added to the entire beams. Now next I'm going to select here. I can go to object, and this time I'm going to select columns. Now in the column I will go back again, the same parts, and here I'm going to go 0, and this time I'm not selecting beam but instead selecting columns. Now here we have in the degree of freedom, which is this internal force caused to deform the structure. Instead of just M3, because this is a column, so mostly the actual force also cause some sort of large deformation such as backlaying or anything. So I use PM, which is the actual force with the momentary. So now I can say OK, and the second end is again 1, and using same method. So I'm gonna OK. So the entire beam column hinge is defined. So what we're gonna do is again go to the define section, and I'm going to the section here is called hinges, and now I want to call show hinge detail, which is previously defined, and show generated parts. So now you can see a lot of hinges defined automatic for the beam columns. So I'm gonna say OK, and one more thing, I can select all, and I want to go to assign frame, and here is one thing is called hinge overrides. So I can assume the default and say OK. So the hinge is defined, override is defined. Now we can work in one window, and I'm gonna 3D, and you can see the entire beam column hinge is defined and everything is done now. So now we want to define the lateral force. So we can give the lateral force like 2000 kilonewtons in one or this 4 frames, and then pushing to until the structure deforms, or 10,000 kilonewtons like this. So that 10,000 kilonewtons force can be distributed in the entire nodes, or also we can add, instead of the load, we can use some sort of displacement in one node and then see how the structure responds. Now we go to the load cases. I want to but before we define load case, let me do one more thing, is defining the mass source, because we will consider the model in the pushover analysis, and then we need to define the mass. So we're gonna go to mass edit. Instead of that one, I'm going to use this method. So 100% the live load, dead load, and 25% the dead load. So OK and OK. Now again I'm going to load case, and I can change the Now the analysis completed, we can go to the result, and this is the dead load displacement. We go to the displacement curve here. I'm going to showing the pushover. Here is the steps, which step you want, and you also can draw some counter to see how the displacement issue. Here is also, you can see BCD, which is already defined in this curve. This is BCDE, or you can showing IOLSCB. Now I'm going to use this one. Apply OK and OK, and you can see some hinges created. If I go to the one of the elevation, you can see this beam here is the hinge, which is IO, and this means this one is the elastic region, so still is this area is elastic. In the bottom column is in the IO, and we can go to the next step. That was the step 3. We total have 11 steps. If I go to this one, and you can see step 4. So that hinge is developed in different region. Let me one of the elevation, go to elevation A. So you can see we have these 2 beams, columns, and number 6, 7, and number 8. Maybe let me do one thing. I go back 3D, and I want to turn off this select all. If I go to rotate this, we can determine, so where is that other like LS or CP, and we can see there is not all this is in green, and I'm gonna further 8, 10. So this is the last one. So that that the green line is green hinges comes to this area, so that means the damage is quite large. So for this we can determine or see the hinge or the hinge forming in the structure. So here in the displacement, it's better to see that pushover curve, and we can see the pushover curve is here. If I go to back to check this one, and we have this first one, the second one, and the last one. So 1 area, 2 area, 3, 4. You can go to 1, and this is 2. From here, this is 2, and this is 3, and the last one. So this is the pushover curve. We can see if the displacement is reached to this area, so that means about between 150 175. So there will be collapse prevention, so the structure will collapse, and this area is totally collapsed, so the structure will collapse. Now we want to then compare with the available earthquake data. If I go to in this plot type, if I go to plot type and defining this one, and the given capacity curve, the bilinear, this is the capacity curve of the structure, and this is the bilinear curve is this one. So that means we are able to rehabilitate the structure in this location, as well as we can say that is the elastic limit area. And now we want to define some earthquake parameters in the latest earthquake. So we suppose that is 1.2. You can go to select here and give 1.2, and the acceleration and the short period or 1 second is 0.8, and you can define the soil. Let's suppose this is a stiff soil, and other parameters will be default. So we will see the bilinear curves and also the other calculated parameters. So we will see that displacement is the maximum displacement here, which is 92 millimeters, and the shear force which the structure can resist or create based on this earthquake, these amounts of shear force in case we have reached to 2018. But the structure capacity is to here we can rehabilitate the existing structure, so it means has a very large capacity. If I want to increase, if it is different, so now you can see it's going to be larger. If I let's go to be 2.5, so what's going to happen? So now it means that this is the structure capacity and this is the earthquake requirements. So what we're gonna do is, it means the structure, if that earthquake is seen or happened, so the structure will totally collapse. So for this we entirely should if the already the earthquake has happened, so the structure will collapse. If it's not happened, but there is probability to see in such kind of earthquakes, so we have to retrofit or increase the structure resistance more higher. Now here is the other parameters which is giving for us, such as the initial stiffness and also the elastic stiffness and the time period of the structure, and also some alpha U strength, and this is called the yield strength of the structure here, and this is the shear or yield force and displacement force we got. So the total structure weight is this one. So based on this weight, which we already defined the load, dead load and live load, we calculate the weight of the structure. So now we can, in case if you have that such kind of structure, you get this one and you will see this and you can interpret this structure will collapse in this area, totally in this area. So this is the end of the tutorial, and this topic is quite advanced and it needs lots of reading and also reference to more and the performance, and also the more about the how the structure behave and how the hinge is created. So the last thing, let me show you one of the hinge behaviors. So you can see the hinge behavior is here. So that means this is elastic, and then again go to the limit parts and going to the alive and then to collapse. So this is one of the auto selected C1 is column 1, which is this one, and the name of the hinges. So it means that column will collapse like this. So this is the end of the tutorial. If you have any question, please put in a comment and I will find time to answer you. If you like this video and you understand this is a value, to subscribe my channel, and please do it, and keep tuned for further tutorials. See you next time.